Hello learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying, Application and Techniques. We are speaking about photogrammetry for the past two classes, and in our last class we focused on aerial photographs and their uses. We started by classifying aerial photos based on the orientation of the camera axis. Then we explored various geometric properties including the principal point, nadir point, ground nadir point, principal plane, principal line, swing angle, azimuth and isocenter. We also learnt how to calculate the photo scale for both flat and uneven terrains. We also discussed how to determine ground coordinates from photo coordinates using similar triangles. Finally, we applied all these concepts in an example calculating the horizontal lengths between 2 points using their photo coordinates and elevations. Important key takeaway was that if the photograph is truly vertical and the ground is perfectly horizontal and we ignore other sources of errors, the scale of the photograph will be uniform. This kind of photo gives a true orthographic projection, essentially a true map of the terrain. However, in real life, these conditions are rarely met. When the ground isn't flat, the photo scale varies from point to point, showing the ground relief in perspective, which causes the relief displacement. This relief displacement is nothing but the shift in the photographic position of an image due to its elevation above or below a chosen datum. If the relief is above the datum, the displacement is outward, and if it is below, the displacement is inward. Typically, the datum is set at a lower level, so most displacements are outward. Hope these points are clear to you now. With this solid base, let us take our studies further in photogrammetry. The objectives of today's module are to get a grip on the concept of relief displacement in photogrammetry and learn the steps to calculate it, and also understand the factors that affect the relief displacement. Next, to calculate the height of an object using relief displacement. Third, to determine the flying height of an aircraft from vertical photographs. Fourth, to understand the importance of photographic overlaps. Fifth, to figure out the number of photographs needed to cover a ground area and determine the time interval between exposures during aerial photography. Let us go over the definition of relief displacement again. Relief displacement is a lateral displacement or shift in the photographic position of the image of an object due to its relief. Yes, very clear for you. Now, kindly refer to the figure 1. A, B and K are the three ground points having elevation HA, HB and HC. And A0, B0 and K0 are their datum positions respectively when projected vertically downwards on the datum plane. In the photograph, the positions of the ground points A, B and K are shown as small a, small b and small k respectively, with ground point K being directly below the principal point of the photograph. Hope you remember the principal photograph definition. Yes, the point where the perpendicular drop from the front nodal point strikes the photograph. Now, if you imagine that the datum point A0, B0 and K0, all in capital, were also photographed along with the ground point, the positions would be small a0, small b0 and k respectively. But here, as you see from the figure, points A and B are displaced outward from their datum position, with a displacement occurring along the radial line extending from the principal point. Specifically, the distance small a0 represents the relief displacement of point A, while B0 represents the relief displacement of the point B. and point small k hasn't been displaced because it coincides with the principal point of the photograph. Now, to calculate the amount of the relief displacement, take a look at the figure 2. This figure shows a vertical section through the photograph from figure 1, specifically along the horizontal line KA where you have to put your eyes on. Let R as the radial distance A from K and R naught as the radial distance A naught from K, and capital R is the distance between capital naught and A naught. Using similar triangles, we can have small f by capital H minus small h is equal to small r by capital R, isn't it? So, from which we can arrive at small r is equal to capital R into f divided by capital H minus small h. Also, from another similar triangle that we can see in the figure, we get small f by capital H is equal to R naught by capital R naught, which gives us small r naught is equal to capital R f by h. So, the relief displacement denoted by D can be easily calculated as R minus R naught, and you know all the values. So, plugging into the above values on D, we get capital R f by h minus R f by h, and by simplifying we get small d is equal to capital R f small h by capital H into capital H minus small h. But there is one more thing that we could do. We can also write capital R from the above derived equation of similar triangles as capital R is equal to small r into capital H minus small h by f, and capital R is R naught capital H by f. Now, substituting these equations individually on the relief displacement D, we arrive at small d is equal to R into capital H minus small h by f into fh by capital H into capital H minus h, which yields small r into h by capital H, and small d is equal to R naught capital H by f into small f h by capital H into capital H minus h, which yields R naught h by capital H minus h. And when we simplify all these, we will arrive at small d is equal to small r h by capital H, or small d is equal to R naught small h by capital H minus h. The one important thing that you have to note in this equation is the capital H and small h should be measured above the same datum. I repeat, the capital H and small h should be measured above the same datum line. From these equations, we can easily draw the following conclusion. The relief displacement increases as the distance from the principal point increases. The relief displacement decreases with an increase in the flying height. For points above the datum, the relief displacement is positive and directed radially outward, and for points below the datum, the relief displacement is negative and directed radially inward. Fifth, the relief displacement for point directly below the exposure station is absolutely 0. So, now let us understand how to find height of object from relief displacement. So, if we know the scale of the photograph, or if you have computed it using some method discussed earlier, we can determine the height of an object like the tower TB as shown in the figure 3. Let us identify how it is done. Take small h is the height of the tower above its base, and capital H is the height of the exposure station above the selected datum that passes through the base of the tower. T and B are the positions of the top and bottom of the tower on the photograph respectively, and the horizontal distance between them is small d. And now, with this information, we can calculate the height of the tower using the scale of the photograph and the relief displacement. Let us do this step by step. At the step 1, we have to determine capital H from capital S. I repeat, at the step 1, we have to determine capital H from capital S. With the known scale S of the photograph and the focal length f, we can determine the height h of the exposure station using the relation S is equal to small f by capital H. Now the step 2. Once we have capital H from this relation, we can determine the precise height of the tower or any other object in the photograph using the equation small h is equal to small d into capital H divided by r. As we know, small d and r already. Yes, that's it. Now let us go through an example to make this clear for you. Imagine we have a tower TB that is 50 meter high. This tower appears in a vertical photograph taken from an altitude of 2500 meters above mean sea level. The image of the top of the tower is 6.35 meter from the principal point on the photograph. The elevation of the bottom of the tower is 1250 meter and we need to calculate the relief displacement. So the problem statement is displayed there for you on the screen. And the solution is like this. Let capital H is equal to height of the lens above the bottom of the tower. The displacement d of the image of the top with respect to the image of the bottom is given by small d is equal to small r h by capital H, where h is the height of the tower above its base, which is equal to 50 meter, and small r is the distance of the top of the tower on the photograph, that is 6.35 meter, and capital H is the flying height above the base of the tower, which is equal to 2500 minus 1250 yield 1250 meter. Now plugging into the value, small d is equal to 50 into 6.35 by 1250 is equal to 0.254 meter or 25.4 centimeter. So the displacement of the image of the top of the tower with respect to the image of its bottom is approximately 25.4 centimeter. Another example for you. A vertical photograph of a flat area having an average elevation of 250 meter above mean sea level was taken with a camera having a focal length of 20 centimeter. A section line capital AB 250 meter long in the area measures 8.50 centimeter on the photograph. A tower TB in the area also appears on the photograph. The distance between the images of top and bottom of the tower measures 0.46 centimeter on the photograph. The distance of the image of the top of the tower is 6.46 centimeter. Determine the height of the tower. So the solution goes like this. Step 1 is the determination of the scale of the photograph. We know that a section line AB in the photograph, which is 250 meter long in real life, measures 8, repeat, we know that a section line AB in the photograph, which is 250 meter long in real life, measures 8.5 centimeter on the photograph, and the focal length of the camera is 20 centimeter. So to find the scale of the photograph, we use a formula scale is equal to map distance by the ground distance, which is equal to small f by capital H. Plugging into the value, we arrive at this equation 8.50 by 250.0 is equal to 20 by h. And solving for h, we get h is equal to 20 into 250 divided by 8.50, which gives the value 588.2 meter. So the height of the lens above the area is approximately 588.2 meter. Step 2 is the calculating the height of the tower. We know the distance between the images of the top and bottom of the tower on the photograph is 0.46 centimeter. The distance of the image of the top of the tower from the principal point is 6.46 centimeter. So to find the height of the tower above its base, we use the formula small h is equal to small r capital H divided by d, where r is the distance of the image of the top of the tower, which is 6.46 centimeter. Capital H is the flying height above the ground, which is 588.2 meter, and small d is the displacement of the tower's image, which is 0.46 centimeter. So putting into the value together, we get 0.46 multiplied by 588.2 divided by 6.46 yields 41.89 meter. So the height of the tower above its base is approximately 41.89 meter. Now moving on to the next topic, that is the flying height of an aircraft. The flying height of an aircraft when taking vertical photographs is important for various calculations. While you can get an approximate value using an altimeter, here is how you can measure it more accurately. So, the method 1 is you can determine the flying height using the scale capital S of the photograph. For this, you need a ground line capital AB of known length that appears on the photograph. The formula is capital H is equal to small f by capital S, where capital H is a flying height above the ground, F is a focal length of the camera and capital S is the scale of the photograph. This method works well when the end points capital A and capital B of the ground line are at the same elevation. However, if the elevation of the two ends differ significantly, the flying height calculation will be less accurate. For better precision, the end points capital A and B should be on a line that passes through the principal point O of the photograph, and their images A and B should be equidistant from capital O. This approach helps to correct for difference in elevation and provides more accurate results. Now, moving on to the next method, that is method 2. If the conditions from method 1 are met, you can still determine the flying height capital H accurately using another approach. This method requires knowing the exact elevation of both endpoints capital A and capital B and the length of the line capital AB. Here is how it works. You need to know the precise elevation of the endpoints capital A and capital B on the ground. You also need the actual length of the ground line capital AB. As we have discussed already in the earlier lecture on ground coordinate, length capital L of the ground line can be expressed in terms of ground coordinates capital XA, capital XB and capital YA, capital YB, and can be given as L is equal to root of XA minus XB the whole square plus YA minus YB the whole square. To find capital L, we substitute the values that we have studied in the ground coordinates under aerial photogrammetry into the above formula. So, we arrive at capital L is equal to root of XA by F capital H minus HA minus XB by F capital H minus HA the whole square plus YA by F capital H minus HA minus YB by F capital H minus HA the whole square. Here what you need to know: the photo coordinate of the point A and B, focal length of the camera and elevation of the endpoints. With all these values plugged into the equation, you can compute the flying height H above the datum very accurately. Let us look into an example for this. A road section of length 1 kilometer scales 82.51 millimeter on a vertical photograph. If the terrain is fairly level, determine the flying height above the ground. Take small f is equal to 152.4 millimeter. Solution is the data that is given in the question. Let us sort it first. So, length of the road section on the ground is 1 kilometer, that is 1000 meter. Length of the road section on the photograph is 82.51 millimeter and the focal length of the camera is 152.4 millimeter. Step 1 is finding the scale of the photograph. The scale S of the photograph can be found using the formula S is equal to ground distance by photo distance, which gives 82.51 mm divided by 1000 meter. So, converting 1000 meter to millimeter, 1 meter is equal to 1000 millimeter, right? S is equal to 82.51 mm by 10 lakh mm, which is equal to 0.408251. which implies S is equal to 0.08251 into 10 power minus 3. Now, calculating the flying height using the formula H is equal to F by S. So, F is a focal length and S is the scale. So, substituting in the formula, we get H is equal to 1847968 mm. So, converting this to meter, we arrive at H is equal to 1847.97 meter. So, the flying height above the ground is approximately 1848 meter. Another example for you, the ground length of a line AB is 610 meter. The measured coordinates on the vertical photograph are XA is equal to 106.41 mm and YA is equal to minus 21.43 mm, XB is equal to 18.35 mm and YB is equal to minus 62.41 mm. If the elevation of A and B are 452 meter and 435 meter, determine the flying height above the datum. Take F is equal to 152.4 mm. So, let us solve this example step by step. Writing down the given data, the ground length of the line AB is 610 meter. Coordinates on the photograph, point A is XA is equal to 106.41 mm, YA is equal to minus 21.43 mm. And at point B, XB is equal to 18.35 mm and YB is equal to minus 62.41 mm. The elevation of point A is 452 meter and point B is 435 meter. Focal length of the camera F is equal to 152.4 millimeter. So, substituting in that lengthy formula and solving the quadratic equation, we arrive at capital H is equal to 1407. Yes, that is it. Having done with the determination of the flying height of an aircraft from a vertical photograph, let us now move to the next topic, that is photographic overlaps. In aerial surveys, vertical photographs are typically captured along flight paths that have been planned to ensure the right amount of overlap between consecutive images. These images are taken at regular intervals to guarantee that each photograph shares some common coverage with one another. This shared coverage, which we call end lap, forward lap or simply lap, is important for creating a complete and continuous map. Typically, the end lap is set between 55% and 65% with an average of about 60%. This means each photograph covers an area that overlaps the previous photograph by about 60%. So, to put it very simple, 60% of the area in one photograph is duplicated in the next one, as you could see in the figure 4. Let us take a look at figure 5 now to understand this better. In figure 5, we have two flight strips, each 2 km wide. If each photograph covers a length of 1 km, then the end overlap between consecutive photos will be 0.60 km. This overlap ensures that there is a 60% common area between two adjacent photographs along the flight strip. You can see this overlap in figure 5, where three consecutive photos cover a part of the small area. Now, looking at the figure 5b, which shows a section along the strip, you will notice how this overlap is managed. Besides end overlap, flight strips are also arranged with a side lap or lateral overlap, where adjacent strips overlap each other. This side lap usually ranges from 25% to 35% with an average of 30%. So, for a 2 km wide flight strip, there will be about 0.6 km of common area between the two adjacent strips. This is easily illustrated in figure 5a for your understanding. Now, in figure 5c, which shows a section across the strip, you can see how the side lap ensures continuous coverage across strips. Additionally, it is worth noting that alternate photos in the same strip often overlap by about 20%. For example, as shown in the figure 5b, the overlap between the first and third photograph is 0.2 km. This overlapping helps in maintaining the accuracy and completeness of the aerial survey. And the advantage of this overlap are: first, complete coverage for stereo viewing. The end lap ensures that each strip is covered from two viewpoints, which is essential for stereoscopic viewing and measurement. Next, useful small overlap area. The end lap creates a small overlap area about 20% between alternate photos. This small overlap is handy for extending horizontal and vertical control using photographic methods. Third, better mosaic. Thanks to the end leaf, we can discard the end portion and use only the central portion of the photograph when constructing mosaic. Accurate type of photos. Overlap helps in accurately tying different photographs together. Then fifth, redundancy for equality. With overlap, each part of the terrain is photographed 2 to 3 times. If a photograph is distorted by excessive tilt or cloud shows, it can be discarded without affecting overall accuracy. 6. No gaps in coverage. Side lap ensures that there are no gaps in coverage. Without it, any deviation from straight parallel flights could leave uncovered portion. At the 7, we have multiple angles for better viewing. Sufficient end lap allows objects to be viewed from more than one angle during stereoscopic examination, enhancing the depth and detail of the analysis. Lastly, we have reject distorted edges. Overlaps let us to reject distorted edge portions of the photograph caused by tilt and relief and use only the central portion for analysis. So, the next objective now is to determine the required number of photographs. To figure out how many photographs you need to cover a given ground area, you can use a net area that each photograph covers. There are two common methods for this. First is using the ground area. If you know the total area of the ground, you can calculate the number of photographs based on this total area. Next is using length and width. If you know the length and width of the ground, you can determine the number of photographs needed by considering these dimensions. Let us look into this quite closely. Method 1. Calculating the number of photographs using ground area. This involves some step-by-step process. So, the first is scale of the photographs, that is mentioned as capital A. This is a key factor. The scale tells you how much ground area each photograph covers. Next is the ground length capital L covered by each photograph. If small l is the length of the photograph in direction of the flight, the ground length capital L covered by each photograph is given by L is equal to 1 minus PL into 1 by S into L. Here PL is the end lap between successive photograph and L is the length of the photograph in the direction of the flight. Next, the ground width covered by each photograph, which is given by W is equal to 1 minus PW into 1 by S into small w, where PW is a side lap between successive flight strip expresses ratio with an average value of 0.30 and small w is the width of the photograph normal to the direction of the flight. Step 4. The ground area small a covered by each photograph. The formula is small a is equal to capital L into W. Plugging into our previously obtained values, we can obtain small a is equal to 1 minus PL into 1 minus PW into LW into 1 minus S square. Finally, the number of photographs capital N required to cover the total area capital A can be calculated using capital N is equal to capital A divided by small a. This gives an approximate number because ground areas are often irregular, making it tricky to plan straight parallel flight strips of equal width. But for rough estimate, it works pretty well. Now moving to the next method. Let's look at the another approach where we use a dimension of the ground area. We'll assume the area is rectangular for simplicity. So step 1 here is the ground length and the width calculation. Let us call the length of the ground as L1 and the width is W1. So the number of photographs along the length N1, we know L is equal to 1 minus PL into 1 by S into L. So the number of photographs needed to cover the length L1 is equal to N1 is equal to L1 by 1 minus PL into 1 by S into L plus 1. This plus 1 ensures we cover the areas near the ends. Similarly, the number of flights N2 is equal to W1 by 1 minus PW into 1 by S into W plus 1. So the total number of photographs capital N is equal to N1 multiplied by N2. So, these steps you can figure out the total number of photographs you will need to cover your rectangular ground area. This method ensures you account for overlaps and edge coverage, giving you a more accurate count. Now, let us see how to determine the time interval between exposure when taking an aerial photograph. The interval, denoted as capital T, depends on two main factors: the ground speed of the aircraft V and the ground length covered by each photograph, capital L. So, the formula is T is equal to 3600 L by V, where L is the ground length covered by each photograph in the direction of the flight in kilometer, and V is the ground speed of the aircraft in kilometer per hour, and T is the time interval between the exposure in seconds. In aerial photograph, getting the timing right between the exposure is very important. Here is how it is usually done: by regulating the exposures. Typically, exposures are regulated by measuring the time it takes from the image of the ground point to move between two lines on the ground glass plate in the viewfinder. The camera is automatically tripped at suitable intervals. This is done by synchronizing the speed of moving grid in the viewfinder with the speed of the image as it moves across the screen using an intervalator. This handy device helps to determine the exact time interval between the exposures, ensuring everything is timed perfectly. So, by using these methods, you can make sure your aerial photographs are taken at just the right moment, giving you the consistent overlap and quality you need. With this clarity, let us look into the another example. Determine the number of photographs required to cover an area of 500 square kilometer. If the scale of the photograph is 1 in 10,000 and the photograph format is 230 by 230 mm. Take the longitudinal overlap as 60% and the side overlap as 30%. The solution is, first we calculate the ground area covered by one photograph using the formula small a. Yes, small a is equal to 1 minus PL into 1 minus PW LW into 1 minus 1 by S square. Repeat, small a is equal to 1 minus PL into 1 minus PW LW into 1 by S square. So, putting into the value, we can obtain A is equal to 1.4812 kilometer square. It means one photograph covers 1.4812 square kilometers. Now, to find the total number of photographs needed, capital N is equal to capital A by A. Putting into the value, we can obtain N is equal to 338, which means we need 338 photographs for this. Another example, determine the number of photographs required to cover an area 25 km by 20 km. The scale is 1 in 10,000 and the format is 230 by 230 mm. Take the longitudinal lap as 60% and the side lap as 30%. The solution is, first we find out how many photographs are needed along the length and the width. We know the length formula N1. Substituting in that, we get N1 is 28.17. When we round off, it is coming to 29. Similarly, for the width, we can obtain N2. N2 is coming to 13.42. When we round up this, it will be 14. So, the total number of photos will be N is equal to 29 by 14 is equal to 406. So, we need 406 photographs. There are 14 flight strips with 29 exposure in each strip. Another very good example for you. Compute the data for the flight plan for the following. Length of the ground along north-south direction is 40 km. Width along east-west direction is 30 km. Focal length of the camera is 1524 mm. Format is 230 mm by 230 mm. End overlap is 60% and the side lap is 30%. And the average scale is 1 in 10,000. Ground speed of the aircraft is 240 km per hour. Flight strips are to be laid out in north-south direction and the two outer strips are to coincide with east-west boundaries of the area. Also prepare the flight map on a base map whose scale is 1 in 50,000. The solution is, first step is finding the flying height above the ground. We know the formula for capital H. So, substituting in that, we obtain capital H is equal to 1524 meter. So the height above the datum would be 1524 plus 300 is 1824 meter. Step 2 is identifying the ground width covered by one photograph. We know the formula for W, and from W we can obtain N2. So N2 is equal to 30 by 1.61 plus 1 is equal to 20. Therefore, the number of flight strips is 19 because 30 divided by 1.61 is approximately 18.63, which we round off and add 1 to ensure coverage of the entire area. So the actual width of the flight strip is 30 by 19 is equal to 1.58 kilometer, and the distance on the flight map is coming around to 31.6 millimeter. Next is the length covered by each photograph. We know the formula for L, so substituting on it we will get 0.92 kilometer. The ground speed of the aircraft is given as 240 kilometer per hour. So using the exposure interval formula, we can obtain the T value. T is equal to 13.8, which means 14 seconds. So the adjust ground distance will be 14 multiplied by 240 into 10 power 3 by 60 is equal to 933.33 meter. And adjust number of photographs per flight line N1 is coming to 44. So the total number of photographs capital N is equal to N1 multiply N2, which gives 880. So we need a total of 880 photographs to cover the entire area. Let us finish this topic over here. And the summary. So what we have learned today is, we learned relief displacement in photogrammetry. We understood that this displacement occurs due to an object's elevation causing its photographic image to shift radially from the principal point. The key concepts include calculating the relief displacement using the formula small d is equal to small r small h by capital H, and determining the object height and flying height from the photographs. We also discussed photographic overlaps to ensure complete area coverage and how to calculate the number of required photographs and the time intervals between the exposures with very good number of examples. Hope you find these concepts clear and useful. Good day. Happy learning.